Hello, this is section 2.4, question number 31. We are asked to prove the statement using the epsilon delta definition of a limit. In this case, we have the limit as x approaches negative 2 of x squared minus 1 equals 3. I like to do these problems by splitting it up into two parts. Part 1 is the pre-work. What we have to do in the pre-work is find a number delta such that if x minus a, its absolute value, is between 0 and delta. In this case, x minus a is the absolute value of x minus negative 2, or when we simplify, we have the situation of the absolute value of x plus 2 between 0 and delta. Then we have the absolute value of f of x minus L is less than epsilon. I like to start with the epsilon part and work through to find the delta part. In other words, I start with this epsilon part and do algebra to find and how do I compare with the delta part. The epsilon part is the absolute value of f of x minus L less than epsilon. So I plug in f of x, I get x squared minus 1. I plug in L, I get 3. Simplify, I get x squared plus 4. Then I factor to get x minus 2 times x plus 2. The absolute value of x minus 2 times x plus 2 is also the same as the absolute value of x minus 2 times the absolute value of x plus 2. Now remember, what we were trying to do is find some comparison for this delta of x plus 2, the absolute value. In this case, I have the situation of an absolute value multiplied by the absolute value of x plus 2. I'm not allowed to just divide the absolute value of x minus 2 to both sides of an inequality. So therefore, what I'm going to have to do is find some substitution that I'll call k so that I can compare. And what I want to do is say for some positive k, let x minus 2, the absolute value, be less than k. Why am I choosing x minus 2? Well, that's this value, x minus 2 absolute value. So what I'm going to do is take the absolute value of x minus 2 less than k. K is a positive number. So x minus 2 absolute value times x plus 2 absolute value less than epsilon. I'm going to interchange this x minus 2 with k. So that means that k times x plus 2 has to be less than epsilon. Now dividing both sides by this k, I have the absolute value of x plus 2 is less than epsilon over k. From before, that's what I'm trying to get to, is this x plus 2, the delta part. So I have the x plus 2, the delta part. So x plus 2 is less than delta. The absolute value of x plus 2 is less than epsilon over k. So this implies that we should try to use delta equal to epsilon over k. Now what we need to do is figure out what values can we use for this k. For k, assume that x is close to negative 2. Because remember, we are looking at the limit as x approaches negative 2. So that means that x minus a, or x plus 2, the absolute value of that has to be close, so less than 1. Why am I choosing 1? Well, because 1 is a nice number to multiply, divide, add, and subtract. I could actually use any number, but I'm going to choose to use 1 because that's a very easy number to deal with. I have then the situation of the absolute value of x plus 2 is less than 1. By the definition of absolute value, I'm going to say that x plus 2 must be between negative 1 and 1. Now this part, we have to be careful. What I have is x plus 2. What I want to compare with is not x plus 2, but x minus 2. And how do I get from x plus 2 to x minus 2? Well, I minus 4 from x plus 2 to get to x minus 2. So what I did was minus each side of the inequality by negative 4. So I get negative 5 less than x minus 2 less than negative 3. And that turns out to be the absolute value of x minus 2 from this side of those inequalities. That's the definition of absolute value. So therefore, I have the absolute value of x minus 2 is less than 5. And I'm going to make that equal to k. Why am I making that equal to k? Well, remember, that's what I'm trying to figure out up here, is x minus 2 is less than k. Well, x minus 2 is less than 5, so I'm going to make 5k. Or x plus 2 absolute value is less than 1, and I have x minus 2 less than 5. So I'm going to make the choice of my delta to be epsilon over 5. Now, in this particular case, it's a little bit different than I've had before because, remember, in order to get this 5, I had to make this assumption about the fact that my epsilon could be 1. So I need to choose delta to be the minimum between 1 and epsilon over 5, whatever's smaller. All right, that's a lot of work, but now we're ready to write our proof. Part 2, the proof. We need to show that our choice for delta actually works. So we always start delta epsilon proofs the same way. Proof, let epsilon be bigger than 0. With our choice of delta, which in this case is the minimum of 1 or epsilon over 5. If x minus a, the absolute value, in this case that simplifies to x plus 2, the absolute value, is between 0 and delta, then we have to show that the absolute value of f of x minus L is less than epsilon. Consider, if the absolute value of x plus 2 is less than delta, then the absolute value of x plus 2 is less than 1. This is x minus a is less than 1. From the fact that we have a minimum of 1 over epsilon over 5, we can say that we're close to x approaching negative 2. So we have the absolute value of x plus 2 is less than 1. By definition, that means that x plus 2 has to be between negative 1 and 1. I subtracted 4 from each term. Now I have the situation where I'm getting to the absolute value of x minus 2 is less than 5. Also, I have that x plus 2 is less than delta. Where did x plus 2 less than delta come from? Well, that's the thing I assumed in the beginning of my proof. Okay, so start with the absolute value of f of x minus L is equal to f of x is x squared minus 1 minus L, which is 3, simplifies to the absolute value of x squared minus 4, which is equal to the absolute value of x minus 2 times x plus 2, which is equal to the absolute value of x minus 2 times the absolute value of x plus 2. And that is less than 5 times delta. Why is that less than 5 times delta? Well, if x minus 2 is less than 5 and x plus 2 is less than delta, then x minus 2 times x plus 2 has to be 5 times delta bigger than x minus 2 times x plus 2. And that's equal to 5 times epsilon over 5 by substituting the minimum of epsilon over 5. That simplifies to epsilon. So once again, we have shown what we need to show because we have f of x minus L is less than epsilon. All right, therefore, by the definition of a limit, we have the limit as x approaches negative 2 of the quantity x squared minus 1 is equal to 3.